Konnichiwa friends, my name is Aisman Smasi and welcome to the week 1 of the intro to DL and GenAI part A, okay? These courses are all about intro to artificial neural networks and tensors too, okay? So I welcome you into my course. Also, I am very bad. I am very sorry for my bad throat as I have a cold and I am very much confident that it would not meant any harm to the audio. So our first quote is from the author Samal as discussed in the lecture which is about defining the meaning of machine learning. So author Samuel defined the machine learning as the field of study that gives computer the ability to learn without being explicitly programmed. So basically Adar Samal was saying that machine learning is a concept and ability that gives the computer to learn something from the data set or the given input without being explicitly programmed. So in this course basically we are going from machine learning to deep learning. And now you may be asking that why deep learning? Well, let's first understand the concept of the deep learning. Deep learning is a subset of machine learning that uses multi-layer neural network to enable computers to learn complex patterns from the data. So basically it's not something else, okay? It's a subset under the machine learning only. and it uses multi-layer neural network to understand the pattern, okay? It's also the same that it's work without being explicitly programming with align with other small definition of learning from experience, okay? Now the question is how basically machine learning fail and why we bring the concept of deep learning and artificial neural network. So first thing first is that if you are into machine learning, you know that the most of the time we end up caught in feature engineering, okay? So like even there's a quote like machine learning is 70% feature engineering and 30% about making the model. So you know that the vast amount of our time end up in feature engineering, and also it also required domain expertise too. For example, if there is an neural problem, then we need an expert who is well provised in organic chemistry. If it's in weather data, we find someone who could feature engineer the weather, temperature, etc. Okay, so this thing required domain expertise. Second thing is that it fails on high dimensional data like audio, images and text. So like you may have never heard of anything done in the audio, images and text in the machine learning. Have you? At most I probably haven't, okay? Like machine learning can solve audio, images and text. The reason is because it's basically a high dimensional data and the machine learning algorithm fails it. Third thing is that it have very limited learning. So like if you will see the curve of the data versus learning, you will see that as the data we increase, the learning also increase, but after a fixed threshold the learning stops and eventually come to decrease, okay? It's like here after a threshold the model overfit more. But if you'll see during the deep learning, if we made the performance versus data curve, okay, here the first machine learning works well, okay, and the deep learning fails. But as we increase the data, at some point the ML learns very less, while the deep learning performance increase exponentially, okay. and here the difference exists between machine learning and deep learning. First is the feature engineering, where the humans select and design features. In deep learning is completely automatic and the model learns feature by itself. Second thing, as I already told, that here domain knowledge is very high. But here in deep learning, the model only discovers patterns automatically, okay. So we don't need here feature engineering. Third thing is that it works very small to medium data set, okay. Machine learning and deep learning requires very large data set for this training. Fourth thing is that you can train images, text, etc, okay. But here in our deep learning you could train images, text, audio, videos, etc, okay. So in short, deep learning performs far better than machine learning on unstructured data like images, video, audio and text. So now the instructor now proceeds with telling that why today is deep learning revolution, okay. First thing the instructor told is that we have now very big amount of data like our Google, Amazon, Facebook, X, they are like big tech platforms, and they have very big amount of data of users, their algorithms, the user interest and their favorites, okay. Like we have very big amount of data today, and that is what deep learning model needs, okay. That's the number one reason we have our deep learning revolution today. Second thing is the rise of GPUs, okay. So GPUs are basically graphical processing unit. They are usually made for games, but now they are the entire heroes behind our deep learning revolution. Basically the whole deep learning revolution relies now on GPUs. We will understand more about it in this video, okay, for GPUs. Third thing is that we have very big and very best algorithm today. So let's understand what are tensors, okay. You could like see it as like ABCD of the deep learning. Like the entire deep learning works with tensor only, okay. So what are tensors? If you want the simplest explanation of the tensor, it's the generalization for scalar, vector and matrix, okay. So like in school you have understand about the scalars and vectors, okay. Scalars have only magnitude and vectors have both magnitude and direction. The tensor, okay, is the entire containerization of scalar, vector and the matrices, okay. Like we have first our rank 0 tensor, then we have our rank 1 tensor, then we have rank 2 tensor, then we have rank 3, 4, 5, 6, 7. We have like n dimension of tensor, okay. So first let's understand what do you mean by 0 tensor or rank 1 or rank 2. First and foremost is to understand is that understand tensor as how much axis needed to represent that number. Okay, like we have one number 8. Okay, how much axis you need? You will say, since it's a number, you could plot it anywhere and write here 8. Okay, that's the exact thing it is written, is that since we need 0 axis, it's an rank 0 tensor. If it's an like list 1845, okay, 1845, how much axis you need for this? Here you will say that you will need one axis, and you will plot here 1, 8, then here 45. Okay, so here you could see that you only need one axis, so here the rank is 1. Okay, here in second we have here two axes. First is 1/2 and second is 8/0. And yes, you need here two axes, let's say here x and y, where here will be 1/2 and here will be 8/0. Okay, so here you can see that the number of axes define the rank of the tensor. Rank 0 is scalar, rank 1 is vector, rank 2 is matrix, and rank 3 we don't have any name, but the entire deep learnings work in tensor only. Okay, in simplest example, it's generalization of scalar vector matrices for multi-dimensional. Okay, here you could see the first we have number, so we have rank 0, we have one list, so we have rank 1, we have matrices, so we type rank 2, we have an 3-channel matrix, so we write here rank 3, etc. Okay, here the shape is very important. Okay, like here there is only one number, so we write it as this shape. Okay, here we have dimension 1, so we write here like this, and here how much number is there in the first row. Okay, here like you could see that we have here rank 2, so we will be writing here two numbers. First we will count rows, then we will count the columns. Okay, here you will see that we have here 3 dimensions. First we have 2 list here, so first we will write here first 2, then for second thing we will write for each rows how much rows are there. So we have like 1 and 2 rows, here also 2 rows, so we will write like this 2, and for each inside that rows how much columns is there. So you will see that 1, 2, 3 for all. Okay, so you will write here 2, 2, 3. Okay, like for example, if you want to count dimension, you need to count the number of spaces are there, how much spaces are there. For example, if it's like this shape, then 1, 2, 3, 4, this will have 4 dimension. If you have like this, you will count the spaces 1, 2, so we have 2 dimension. Here we have 1, 2, 3, 4, 5, so we have 5 dimension. Okay, to calculate the dimension we need to count number of elements in the boxes. So second is the naming part, where here the elements wise operation will be connected to some naming part in the deep learning. Okay, so here like we have an shape here 9, 3, 64, 64, and in deep learning part you are given the respective name of that column. Okay, so here you will see that first 9 will be batch, 3 will be channel, sequence will be 64, and element will be 64. The how we will say in the tensor part is that there are 9 batches, and each batch have 3 channels, and each channel have 64 sequence and each sequence have 64 elements. Okay, so this is how we name a channel. Here also you will see the exactly the same. Here the shape is given as height, width and channel, and it is given as 2 2 3. Okay, first the 2, then inside the channel we have like here 2, here 2 elements, and inside that element we have 3 elements. Okay, so we say it exactly like this, that we have height equals to 2 and each height have 2 width and each width have 2 channels. Okay, we say it like this only. Then we come to the create tensor path. Okay, since you now know what the tensor is, so let's now create the tensor. Okay, so here you will see that we have 5 ways of creating a tensor. Okay, first from a number directly from input, second from NumPy, third is tensor like exact values, fourth is tensor but we arrange a number in a particular order, and fifth we have matrix. Okay, this is matrix 1. So first let's go to our Google Colab and first import torch. Okay, so this torch means importing PyTorch. Okay, importing PyTorch. So here you will see that this runs successful, and you will print the version of the PyTorch. Okay, so you will see that is the version of 2.9.0, plus we have here CPU runtime informant. Okay, so first we create from numbers. Okay, so here you will see that we directly create from numbers using torch.tensor. Okay, so like we want to make 5 and tensor, we directly torch the tensor and inside the bracket we pass 5. Okay, so you will see that here T0 is in tensor with element 5, and here the size is null. Okay, as I have said earlier. Here in 1D tensor you will input and list here like 10, 20, 30, and here after printing you will see that you got this tensor, and here this size you will get is 3. Okay, like this 3, and here is, since here it's empty, it is not shown. For to this tensor we pass here an entire matrix. When we print we find that the matrix become a tensor, and here the size is 2 by 3. So like we have 2 rows and each rows have 3 columns. Okay, so it's 2 by 3. Now 3D tensors, basically first we have 2 rows here, then for each rows we have two rows as element, and for each rows inside it we have 3 columns here. Okay, so the size become 2, 2 and 3. Okay, so this is the exact way how you create a tensor from numbers directly. Okay, second comes from the NumPy. Okay, so for example, if you have a NumPy array as 10, 20, 30, you directly convert to tensor using from NumPy function. Okay, so here you will see that first I import NumPy, then I make a NumPy array and pass as from NumPy, and we get the tensor array. Okay, third is we want to create tensor using exact values. Okay, so for example, if you want a tensor with all values as 0, we pass as zeros. For if we want 1, then we pass as ones. If we want empty, then we pass empty, and if you want n value to entire graphs inside the tensor, we will use the full. Okay, so here you will see that first I use the zeros to create an 2 cross 3 matrix tensor of a 2-dimensional tensor. Okay, here you will see that all the tensor elements are 0. Second, I create using ones here, and you will see that all the values are ones. Here, if you use the empty one, we basically use any garbage value or from the memory which was there before. Okay, so it's like an garbage value that is taken from the memory. Okay, so we make here 2 cross 3 matrix tensor and we get this value. Okay, D is the full number with given number. So for example, if we need 2 cross 3 matrix tensor and I want to fill 7, I first pass the shape, then with comma I write the number here and I will get the full tensor here. Okay, like this. Then comes the arrange number tensor. Okay, so here we will arrange the number from in starting position to end position, and we could also specify this step size, the linear space or the exact spaces between these elements. Okay, so for example, first here I passed here arrange from 0 to 10 and we take step size 2. Okay, so it will run from 0 to 2 to 4 to 6 to 8. Okay, it's like this, and here the number will go from first element to n minus 1 only. Okay, so you should remember this. So here if it's like 0 to 10, it will go from 0 to 9 only. If I would have passed here 0 to 20, the arrange would go from 0 to 19 only. Okay, second comes here the linear space, where the value is differentiate between and chunks. Okay, so for example, if we have here start 0 to 10, we will divide 0 to 10 number line into 5 chunks here. Okay, and we will get these values. This is how linear space works. If you want log space here, it's go from here, like I could say here, if it's here 0, then it will go from 10 to the power 0 to 10 to the power 3. Okay, and here this space between will be 4 chunks. So we will get here exact 4 points here. Okay, this is how the log space works. Fifth, we have the matrix 1. Okay, so for example, if we want an identity matrix, we pass here the I, so you will get the identity matrix of 3 dimension. Okay, if we want for diagonal matrix, we pass the tensor and it will create an diagonal matrix for us. Okay, here. And if we want like any random tensor, okay, we will pass here toss dot rand, and here we pass the matrix dimension and it will create the tensor here. Okay, this is for the random tensor. And if you want the random normal tensor, okay, for the normal distribution, we here RANDN we pass it. Okay, here N stands for normal and it will return an normal tensor here. Okay, so this is the whole 5 steps on how we create an tensor. Okay, then here, so now comes here the hardware acceleration in tensor. So like in the first question you may be asking during the start of the lecture is that why we need tensor. Okay, what's the use? Okay, so first let's understand what's this. Okay, so have you seen this structure and do you know the name of this device? If you have guessed correctly, this is an GPU, okay, by NVIDIA. So the reason why we use tensor is that the tensor could work in GPU, okay, instead of CPU. Here, unlike NumPy, the tensor could live in CUDA and could be trained in parallel. Okay, so first understand what is CUDA. Okay, CUDA stands for Computed Unified Device Architecture, which is NVIDIA's parallel computing platform. So basically there was an age like 10 to 20 years ago where the entire matrix calculation or the hardware acceleration were all done by CPU only. So you could see here that here is an CPU which have here multi cores. Like for example, you have like 2, 3, 5, 7 cores GPU here. I mean cores here in CPU. Okay, so the entire here arithmetic operations or matrix multiplication take place inside CPU only, which have only 2 to 15 to 20 cores here. Okay, and it's not a very great deal, but after NVIDIA making GPU here, we have like tens of thousands of cores here, and we could also process here parallelly. Okay, so for example, if you have like 1000 matrices all of equal 1000 length, here we will multiply all them parallelly, so it saves our time and even give us a huge computational power here. Okay, so this is the exact reason why we use tensors here. So you may have also seen here many memes like here AI running on CPU, which shows an Zootopia sloth bear, and like if you run the AI on GPU, it's become one of the fastest man on planet. Okay, so this meme clearly show the difference between CPU and GPU. Here we also have another meme where we see that how computer processor works. How so here we also see that how computer processor works. So here you can see that here we have an truck, and here this CPU only one person pulls it. Okay, but here during the GPU even we have an huge aeroplane. Here many people pulls it. Okay, so if you really want to see the wonder of GPU, consider in question. Suppose I have 5 lakhs into 50 lakhs two matrices. Okay, so can you tell me the exact time between CPU and GPU on how much time it would take? Think again. I hope you have answered this correctly. So here is the exact answer. Okay, the CPU would need it 24 hours. For GPU it's just 1 second thing. Okay, so by this comparison you could really see the power of GPUs. Okay, if you want some more comparison, you will see like it will take 15 seconds in CPU while it will take 0.1 second in GPU. In other case it would take 1000 years in CPU while it would take 1 day in GPU. Okay, so you could clearly see that GPU is a whole superpower. So you will be asking, so how we send our tensor to GPU? Okay, first you will see here that we have to find here that if our device support CUDA or not. Okay, so we will find it by tos.cuda.e/available. If it's come true, then we have our GPU. If not, then we don't have our GPU install. Okay, if you are in Google Colab, you will see that we actually don't have CUDA. Okay, so we change our runtime here to an GPU here, GPU here, and then we once again run our program. So let's see, now we have CUDA support or not. Yes, so now it's been true, means now we have our CUDA support available. If you are also on Kaggle, you will also see that there's an option to change the runtime to an GPU. If you are doing this in an PC, you must download the NVIDIA CUDA support from their website. Okay, here in NVIDIA you will see the supporting system, and if you are Windows or Linux, you could download it from here. Okay, the CUDA support. For now I have CUDA support available, and here by tos.cuda.get device name /0 you will find the exact name of your GPU. Okay, second thing is that how that you have to first define a device which will work in CUDA or else CPU. Okay, so first we initialize in device. Okay, so here we define it by toss.device, where we pass CUDA if the toss.CUDA is available. Since it will be always true, we will have our CUDA support in this device. Okay, in this device. If for some reason we don't have CUDA support, then it will not raise any error. Instead, the device will be used as CPU only. Okay, so how do you send a tensor to CUDA? Okay, so so first step is that you use the x.to device. Okay, tensor.to device here, and this x now will be residing in the GPU only. Okay, we also have another one where during our initialization only we put in comma and we write device as CUDA. Okay, here we have two methods, and we could see that the x is now in the CUDA. Okay, so here now you could see some tensors operation in GPU, where we first make an toss dot any random matrix of 3x3 and we send it to our CUDA, then we plus it and then we check whether C is in CUDA or in CPU, and we see here that the value print is CUDA. Okay, so this is basically how we first initialize and CUDA, then we set devices CUDA, and then we send an tensor to CUDA. Okay, you may be asking that how to like send the device from CUDA to CPU. So the format is exactly the same, is that you type dot here and type here CPU. Okay, and the entire tensor come back to here CPU only. Okay, now here there's a question here, is that we have an tensor here in CUDA. Okay, then we have here another tensor here which is not in CUDA, and we are trying an arithmetic operation. Okay, so do you think that the operation will be successful or not? Please answer about this. Think and answer. This is from the PYQ September 2025 done. Okay, quiz 2. Have you thought about the answer? So the answer here will be no. Since here one is in GPU and one is in CPU, this thing can be proceed and it will raise an runtime error. Okay, here runtime error. So you must have understand that why we use tensor. Okay, so here the tensor is basically NumPy plus superpower. Okay, and what is that superpower? The superpower of GPU here. And tensor also have another superpower, and that is auto gradient. Okay, we will see this in our upcoming things. For now, let's get into tensor manipulation. Okay, this is the most important part here. Okay, so first, how we will be manipulating our tensor? Okay, so first we could do here reshape here. Okay, so first we have dot x here, which is like 1 2 3 4 5 6 in 3 cross 2 matrix. Okay, so we first view here the entire matrix. Okay, we could also reshape it. Okay, like here 1 row into 6 column, so here the entire matrix will be reshaped. Third, we have like x here dot unsqueeze. Okay, this is very much important. Please see here if we do an unsqueeze. Okay, so for example, if we have here like 2:1, if we do here unsqueeze, it basically acts at an new dimension here. Okay, at first if we do unsqueeze, and then if we do squeeze here, we get back our old element. Okay, so for example, if you 2 cross 1 here, if we do unsqueeze, we get here 1 by 2 by 1. Okay, so basically it adds an extra dimension here. When we here unsqueeze again, we get here 1 by 1 by 2 by 1. Okay, so basically in short, the squeeze here basically adds an extra dimension here. Okay, at first, and here the wider squeeze remove that dimension back. Okay, so this thing is very important, and it will be helpful in our CNN videos. Okay, second thing here is that we have here indexing and slicing. Also in our like collab, I have like whole code ready to view. Okay, here the entire thing, the squeeze and unsqueeze here. Second thing here is the indexing and slicing. So for example, we have this matrix as tensor. If you want to, if we write here 0, it takes the first row. Okay, if we write here 0 by 2, okay, so it will check your first row and second number column. Okay, so here it is 0 1 and 2, so here the 3 comes from here. Okay, it's basically like slicing here. Here slicing here, we take here x, here we take the entire one, and we take this second column here. Okay, so here we took the entire one, but we took this second column here. Okay, so it's come to be 2 by 5. Now coming to the mathematics operation part. So as you could see that we have a matrix here. When we do x plus 10, basically here if there is a scalar, the scalar get added to entire element of the matrix. So for example, if it's here 1, then we get 11, for 2 we get 12, and so on. Okay, so like for scalar, the addition is cumulative. For same for example of multiplication, if we have here scalar multiply the each element multiply to its respective element. Okay, so like you could see here I had 10 and that 10 is added to each one part. Okay, and if we multiply to 2 we get multiplication 2 for each element. Okay, so now you may be asking, what if I want to sum all the elements inside the tensor? So you could easily do by x dot sum. Okay, so if you will x dot sum, basically summation of the whole tensor. Okay, we get here sum of all values in the tensor. Also we have here another concept called broadcasting. Okay, so for example, if you have we have like 10, 20, 30, so how it add, you could say that I have here 1, 2, 3 and 4, 5, 6. Okay, 2, 3, and I add here 10, 20, 30. Okay, so 10, 20, 30. So 10, 20, 30. So basically what it does is that first element it plus we get here 11, then second we have 20 here, so we sum that element and we get 22. For 3 we get here 33, we get, it was 30 now, so we get here 33. Okay, for first row. For second row we also multiply the exact thing 4, 5, 6 with 10, 20, 30. We get here 14, 25 and here 36. Okay, so basically here the thing is here it's called broadcasting, where for each rows we sum the values here. Okay, it will happen same for multiplication too. Okay, so like if we add here into you will get the exact same thing here. Okay, then we have here concatenation and stacking. Okay, so let's delete this one first. So here if you want to join two tensors, we have here two options. First is using cat here, which basically make it into an single tensor. Okay, so for example we have 1, 2, 3, 4, it will add as an list. Okay, so for example here we have tensor, here we have tensor, the cat thing will add the both to an list. For stack, it will what it do is that we have an here element, then it will stack the entire thing. Okay, you could see here clearly is that we have here 1, 2, 3, 4, so it joins them and here it wholly stacks them together. Okay, so there's the difference. Here dimension equals to 2 means this stacking or concat is done row wise. Okay, not column wise. Then we also have here transpose here, and if you have like learnt about linear algebra, you know that for a matrix stacking basically interchange change the rows with column. So for example, if a 1 2, we write here 1 2, and 4 3, we write it in column 4 3. This is how it works. Okay, so it's also very simple. In previous we have like 1 2 3 4 4 5 6. Now we got as rows and columns interchange. Okay, here this one is also easy. You how to send the tensor to device, then back to CPU. Okay, this is also the same. And here in L we have like most important thing called cloning and reference. Okay, so like you may have done two operations here. First is that x equals to x or x equals to x dot clone. Okay, here the main point here is that if you are doing x equals to x, okay, so here basically is referencing the data set. Okay, and here if we done that x dot clone, then this is one of the safest part, and we basically clone the thing. Okay, you could see here clearly. Okay, let's see, we have an tensor 1 2 3 4 5 6. Okay, we first clone it, then we change the first element to 99. Okay, you will see that only the x1 element change. Okay, after this the x1 element change because I cloned it. I don't reference it like here. Okay, but if you will doing like reference here, let's see. Then you will see that the both x and x1 changed here. Okay, so basically here is basically a danger thing which is basically called referencing. So if you are directly doing this, the x1 is not cloning but referencing. If you do anything with this data set, this x will also change. Okay, so with this we come back to our matrix multiplication. It will be doing here the matrix multiplication here. Okay, and here the command is mat multiplication. Okay, mat mul. Okay, this is how basically tensors multiply. Okay, so for example, it's like we have 1 2 3 4 here as one matrix, and here we have 5 6 7 8 here as another matrix. Then the resulting will be the matrix multiplication of the column. Okay, so we have here in the very last here. Okay, here we have in the very last here. Then we have here sorting and the top k function. Okay, then finally we have here this sorting option where we use the sort here. Like here we have like 3 1 2, then this sort function will sort it in increasing order. Okay, this sort, and here the top k here if you have a matrix here like 10 50 20, the top k will choose the top two values from here. Okay, so we will get here 50 20. Okay, here like this. So this is all about the matrix arithmetic, etc. Then we have here the important function called the autogradient here. Okay, like we have learned about this here that tensors have both NumPy plus superpower of parallel processing plus also have the auto gradient properties that we are here learning now. So basically what is this? So basically in tensor we have the property that the tensor computes gradient of tensor during back propagation. Okay, so the entire gradient the tensor will be learning from behind. Okay, it have that property, and it's basically defined using the here requires gradient dot equals true. Okay, this is how we turn on the gradient for an tensor. Okay, here you will also see that requires gradient equals to true. So what happens if we start the gradient equals to true? Okay, so for example, we have here an arithmetic operation y equals to x square plus 3x plus 1. Okay, here we save as y. Okay, here when we do y dot backward, okay, this do an back propagation to x here. Okay, and here this value will compute the gradient here. So to find gradient, we do the derivative with x here. So here x square become 2x and 3x become 3, and since here the value was 2, we put x equals to 2 inside this value and got the gradient as 7. Okay, so basically this is how the auto gradient work. When we do the y dot backward, it computes the gradient, or in short it calculates the derivative of x. Okay, here you will see the exact output. What would happen if we had two gradients here? Okay, so for example, here first here you will see that here also a new question. Here we define x as tensor which is equals to 2. First we do x equals to x square, then we do y equals to x cube. Okay, so when we do here back propagation, okay, 2 times here we calculate the derivative. Okay, and here since the value of x was 2, we get here 4, and for 3x square which we got from derivative, we got as 12. Okay, but here since we have not clear the gradient, we get the value as 16. Okay, so here 4 plus 12 equals to 16. Always remember that you should do this. Okay, then only we get here 4 and 12 value. Okay, if you are not making gradient equals to 0, the value jumps to our new back propagation, and we get this value. Okay, so here I had also showed about that. Yes, here. Okay, so here also you had seen that we have like here x square, x cube, and here we get the 0 gradient. Then let's do it again. Okay, here you see first we get 4 here, then here we should be getting here 12, but we get here 16. Okay, but here we clear the gradient and then we do it again and got this value. Okay, get the exact 12 value here. Okay, so here the x dot gradient dot 0 slash function is very important if you want to remove the gradient. Okay, also how you will stop the gradient? So here the answer is that with toss dot no gradient dot as in function. Okay, so here here like this one. Okay, with toss dot no gradient, and here you will write the exact same function here. Okay, and here the gradient would not be calculated for x here. Okay, so this is how you stop gradient. Also you could detach gradient using tensor dot detach. Okay, so this is the whole thing about gradients here. Then coming to the NumPy and tensor integration. Okay, so here the auto gradient complete, and we have our final two chapter for our part A, and first is the NumPy and tensor integration. This one is easy, that to convert an tensor to NumPy we use dot NumPy function, and we will get the NumPy array. And for NumPy, if you want to convert to tensor, we use from slash NumPy, and we get the tensor operation here. Remember that if here the tensor is in GPU, then it will raise a runtime error, as NumPy only works in CPU only. Okay, so here we first detach here, then we make the tensor to our CPU, then we convert to NumPy. Okay, so if the tensor is in GPU, then this is an safe option here. Okay, safe option here. Okay, so we could see here, we first make a NumPy array, then we convert to here tensor. Okay, you could see here the exact value. Then from tensor to NumPy we use the tensor dot NumPy function, and then we get the exact value here. Okay, then comes the reproducibility part. Okay, so like during our research or practical submission, we need our random values need to be consistent. So like you have here learn about how to create an tensor of an random value here. Okay, this one. So here if you like call this function, we get random values each time, and to stop getting random values for different runtime environment, we here do the reproducibility part. Okay, here like here you could see that I am creating a 3x3 matrix here, and no matter how much time I type, you could see here that I am always getting an different value each time. But during our research or practical submission, we need our random values to be consistent. Okay, we don't want to change this during each runtime here. So what we do here is that first we import random, and then we fix the random speed seed to an particular value here. So random dot seed here, then NumPy also we do the same, then for torch also we do the same, and for torch GPU we also do the same. And this exact 5 things makes the reproducibility very much reproducible. Okay, so for example, we fix here as seed equals to 42, then we here do. Okay, here you will see that no matter how much time I type this, I will get the entire the same value. Okay, here 0.82233 with like 33 and 0.8823. okay, here once again you could see that. So this random series is very important during running netbook once again to get consistent value. Okay, this is important during research or during the practical submission if you have used the if your code rely on the random values. Okay, so that's all for today, and see you in part B of this DL and GenAI course, where we'll see about the how to make a linear regression using PyTorch, the fundamental tricks, and the activation function. Okay, so that's all for today. Thank you. Bye bye.